Okay, before I go on to task 4, very quickly, I wanted to show you how if a user enters multiple vectors of information, how the program will check for that, and it will prompt the user to enter the same number of elements per vector. Let me run this real quick. Actually, let me stop that. And let's start. And let's say we entered mole fraction 0.1. If the user decides to put a vector in for this quantity, and then put 0.4. So since the number of elements do not match, the code will prompt the user that the dimensions of the vectors are not the same, and the code will ask to re-enter values again. I'm going to stop this now so I can show you the last part of our code. Last part of our code deals with utility cost, which was given into our problem, and it was to find the cost to cool the gas coming out of the reactor and the cost to condense the ammonia, which would be right around here. So gas is coming out of the reactor, go into the cooler, and this is the condenser, and ammonia is condensed and taken out. So the cost to cool the gases first, and then to condense ammonia. This was given into our problem equation right here, where the gases leaving the reactor at 450 degrees Celsius. They come out of the cooler at -20. The heat of vaporization is given for ammonia, and the heat capacities are given for each gas. And the cost of cooling is $17.68 per megajoules. So in order to find this, we had to use energy and enthalpy equations. I have solved them over here. You come down to see delta T is -470 Kelvin, and the equation that we're using is this one, Q out. So first we do is we find the energy that is required to cool the gases coming out of the reactor, and that will be the Q out, and that is the sum of the energy required to cool each part of the gas. So in order to do that, we find the number of moles of each element, and then we multiply them by this equation, and that will give us the energy that will be needed to cool the gas from 450 to -20. After that, all we're concerned about is inputting enough energy to vaporize, condense ammonia and to vaporize the rest of the gases. So we're only concerned with ammonia. So at this point, the HVAP refers to kilojoules of energy per mole of ammonia. In total, the whole energy input will be the Q, which is Q out, plus Q vape. And then we multiply that by the cost given over here, $17.68 per megajoule. Keep in mind the unit conversion from kilojoules to megajoules, and then we will be able to find the total money that will be required in order to cool or in order to produce that much ammonia. So this part of our code is user dependent. Whatever the user enters, we will use those values to find. In this equation, the N_N is the molar ratio of the gas. So it could be 10 moles per hour, it could be 5 moles per hour, it could be 6 moles per hour, depending on the user. Xi naught is the same as before, FSP is same as before, YP same as before. And right over here, first we do is we set our variables or constants, the enthalpy constants, for heat capacity constants. They are in joules per mole times Kelvin for nitrogen, the inert gas, and ammonia. This is the DT is the temperature change difference, and HVAP is also the constant, joules per mole for ammonia, and the cost is dollars per megajoules. In this part of the code, since this code is supposed to repeat until the user wishes to exit, we put it in a while loop and we set a counter q equals 1. It's actually the menu that the user will answer at the end of each run. And if the user chooses yes, this loop will continue and the user will enter the values again and it will calculate and display the answer. And it will continue to do so until the user hits no. So let me give you a demo. Let's say we run this code. We pick a rate of 4 kilomoles per hour. Enter the mole fraction of the inert gas, 0.4. Fractional conversion, let's go with 0.9. And the fraction of the gas leaving the condenser, let's go with 0.2. So at the end of this, we get the total cost of cooling at that rate is $2,326.81 per hour. That is the cost to condense that many moles of ammonia. And at this point, you can see that if the user wishes to enter other values, you can hit yes or you can hit no. If you hit yes, you will restart and it'll ask you the values again. So let's say if we enter different values this time. And it will give us a different amount for cooling that much ammonia. Now, let's say if we want to, then if the user does not wish to repeat, we just hit no and it comes back up to where it calculates. And then now we can see our values and our variables. So at the end of this, what we have realized is that in order to cool ammonia and see the relationships, first part of our code works and our last part of our code defines the utility cost for ammonia production. And the code is valid for many situations where the information is given in just these variables. If other variables are given, the equations will change and this code will not be valid. So the only application I guess I could think of is that if a person knows the mole fraction of the inert gas, or the fractional conversion of the reactor, and the fraction of the gas leaving the condenser, then and only then the person can use this code and find out the number of moles of individual gases and the total moles of ammonia produced and the fraction of overall nitrogen conversion. Apart from that, if some other variables are known, this code will not be used. This code cannot be used for any of that. And the units must also be entered accordingly in the second part. So the number of moles coming in must always be entered in kilomoles per hour. Any other units for that will not be compatible with this code. And I believe if I'm come across with any other question like this, I will be able to use this code only if I have these variables. But from that, I hope you like my presentation. Thank you.